In the last class, we saw how this differential amplifier came into being, a sort of story. And then we also understood how the signal Vi1, Vi2, general differential signal, can be split into two components. One, the differential component divided by 2 plus the common component. Another, the same differential component by 2, but with a negative sign, plus the common component. So, what happens is Vi1 is strictly speaking equal to V differential, okay, I differential by 2 plus V common, and Vi2 is minus Vi differential by 2 and Vi common. So, any two general signals can be treated this way. Okay. That means, for any two signals, general signal, there is a common component and there is a differential component. So, we can analyze the differential amplifier for the common component first. This should not be amplified at all, and then the differential component, which should be amplified, and then superimpose, okay, one output over the other and get the total output. Yesterday we did the analysis by considering Vi1 is equal to Vic, Vi2 equal to Vic. Then this becomes symmetric, and then we saw it can be split into two separate circuits, each containing 2 Re, 2 Re in series with emitter. And then we concluded that the common mode gain is, okay, minus Rc divided by small re plus 2 Re, and you can make it very low by making Re very large. This was the conclusion. Today we will see what happens when we apply only differential signal without any common mode signal. That means, we have to apply Vid by 2 and minus Vid by 2 to the two inputs Vi1 and Vi2. So, let us do that. So, now the circuit is going to be considered with only differential mode signal existing and common mode signal being 0. So, what happens to the circuit? This is an important concept, and therefore, let us see what happens exactly. When we have here Vi1 equal to, okay, Vid by 2, and this one we have minus Vid by 2 applied. There is no common mode signal at all. Now, again this is a symmetric circuit. As far as this part of it is concerned, it is still symmetric. To one end you are applying certain positive voltage, to the other end same value but negative. So, what should happen to a common terminal? You are applying in a symmetric circuit, okay, if you apply a positive voltage, suppose this changes by delta V because of only that positive voltage. If you apply a negative voltage to the other end, what will happen? This will decrease by delta V. So, the effective voltage change here, if you apply positive at one end and negative at the other end to any symmetric circuit corresponding to a common point here, okay, is going to be 0. That means, this will remain at the same state at which it was originally existing without having anything applied at all. That means, this will remain at the quiescent state. Is this clear? So, this is the property of symmetric circuit that we are going to use. What does it mean? Actually speaking, therefore, if there is an increase in voltage here, that increase in voltage should be contained within this itself, and the decrease in voltage by the same amount should be contained within this itself, okay? And therefore, nothing happens here. This remains at the same state at which it was existing earlier. Right? So, this will continue to have whatever current it had before applying the signal. Okay? So, there will not be any change in current through this resistance. Is this clear? There will not be any change in current through this resistance. What is this point therefore equivalent to AC wise? If this is an AC signal, this is remaining at a constant voltage. So, this is equivalent to ground potential. So, since this has remained at a constant potential, whatever this varies, this will vary by the same amount in the opposite direction, then this will remain at quiescent point, okay? And therefore, this has no variation. That means no variation with respect to ground. That means this is at ground potential AC wise, signal wise. So, signal wise picture is going to be simply that we have VID by 2 ground, okay. This is minus VID by 2 ground. This is the signal picture as far as differential signal is concerned. This potential is going to remain unchanged. So, once again let me tell you that in a symmetric structure like this, if I excite one end of this input, okay, by some voltage and some change is caused here, whatever be the change depending upon the opposite polarity change will be caused by applying a opposite voltage by the same amount of magnitude, okay. So, this change occurring at this point is going to be 0, no change will occur, which means this is going to be in effect equal to ground, being at ground potential. So, we therefore see that even though I have physically connected a resistance Re, this Re has no effect on the differential signal. This Re has effect only on common mode signal. So, you now have, as far as differential signal is concerned, VID by 2 and minus VID by 2 applied here, this is grounded. So, these are equivalent to 2 separate common emitter amplifiers. So, you can analyze, okay, differential amplifier as 2 separate common emitter amplifiers, okay, and then find out the outputs of the individual amplifiers. Okay. So, we know that the output of this corresponds to minus GM into RC, okay, into VID by 2. There is a phase shift of 180 degree, minus GM into RC, and this is minus VID by 2. So, this output will correspond to, this is VC1, okay, delta VC1 will correspond to this, and delta VC2 will correspond to VID by 2 into minus GM into RC. So, plus GM V into RC into VID by 2. So, you get the same value of output voltage, but with a phase shift of 180 degrees. Okay. And therefore, if you take delta VC1 minus delta VC2, which is nothing but, okay, V naught as marked there, okay, this is V naught, is going to be how much? Minus GMRC into VID. This is what I told you, okay, earlier also, that the gain of a differential amplifier, the differential mode gain of the differential amplifier, this is nothing but what is this equal to? AD, differential mode gain. AD is defined as the differential mode gain. AC is common mode gain, that we have already evaluated in the last class. So, AC is equal to, how much is that? Minus RC divided by RE plus twice capital RE. Now, this is for what? single ended output. Do you remember that? Because differential output, it is still 0 by symmetry. Okay? AC is 0. But for single ended output, okay, minus RC divided by RE plus 2RE. For differential output, this is called differential output. Therefore, the gain is GM into RC. What is the gain for single ended output? AD for single ended output. That corresponds to GMRC by 2, whether it is here or here. And CMRR, what is this? Common mode rejection ratio. Common mode rejection ratio, CMRR, henceforth. Very important parameter associated with the differential amplifier is ability to what? Distinguish between common mode and differential mode signal. Okay? That is a measure of its ability to what? Dissociate itself from the common mode signal and associate itself only with the differential mode signal, and that in this case is GMRC by 2, GMRC by 2 divided by, okay, RC, okay, slash RE plus 2R. Okay. This RE is equal to 1 over GM. Okay. So, you see that it is independent of what? RC. It is independent of RC and it is equal to, okay, GM into, this is equal to, how much is it? GM into, this goes up 1 over GM plus 2RE, okay, divided by 2. This therefore, normally is going to be equal to 1 plus, okay, 2RE into GM, okay, by 2. This is the common mode rejection ratio of any differential amplifier. So, an important thing that one you can neglect. So, it is equal to GM into RE. If it is a good common what is the differential amplifier, obviously you want this, okay, ratio to be very high, and therefore, this one can be neglected. So, it is strictly speaking GM into RE. So, please remember this, the CMRR of any differential amplifier which is designed properly will correspond to GM into RE. The gain, differential mode gain, corresponds to GM into RC. Okay. So, these are things which you can quickly remember and assess, okay, without doing much of, okay, calculation, etc. So, GM into RE is the CMRR. Okay. So, this is the evaluation of what is called small signal performance of your op amp, of your differential amplifier. What is the effective output? Effective output corresponds to, let us say, single ended is equal to the differential mode gain into differential mode signal plus what? Common mode gain into common mode signal. This is the total output now. The effect due to that analysis plus the effect due to this analysis now will be the combination of the effect due to differential output, effect due to the common mode output. Or what we really want in a good differential amplifier is only this, what is it? AD into VID. The rest of it is the error. 1 plus, this I am taking out. So, this becomes AC divided by AD into VIC divided by VID. This is the error due to finite CMRR, because AD over AC is defined as CMRR. This is normally assigned the symbol rho. So, AD over AC, this is nothing but AD over AC. Therefore, we see that this error is 1 over rho. Now, you can see the significance of this differential amplifier analysis lies in estimating this error. Let us assume that VID is of the order of 1 millivolt. I have differential voltage of the order of 1 millivolt superimposed over a common mode voltage of 1 volt. So, this is 1 millivolt, this is 1 volt. That means, this factor VIC by VID is already of the order of 10 to power 3. So, as an example, VID is 1 millivolt, VIC is 1 volt. So, VIC by VID is equal to 10 to power 3, and I say that the error should be less than 1% for my differential amplifier. So, error epsilon should be equal to 1 over 100. Error should be less than 1%, I say, then epsilon should be 1 over 100. So, what should be the rho in order that error is 1% for a signal which is going to be worst case situation only, when the differential signal is 1 millivolt, the common mode signal is 1 volt. How much is that now? So, what should be the rho? Rho should be greater than 10 to power 5, or in terms of decibels, how many decibels is that? Should be greater than 20 log 10 to power 5, which is 100 decibels. Is this clear? 20 log 10 to power 5, or it should be greater than 100 decibels. So, if you are told design a differential amplifier with CMRR greater than 100 decibels, then you know, right, that is how to go about designing it, and what kind of signal it can handle also you know, right. What kind of error will occur depending upon the signal. So, please remember that you should always consider this effect. For example, a practical commonly encountered problem is your problem of measuring differential voltage in the case of cathode ray oscilloscope. If you want to make measurement, then if you are making measurements of the order of 1 millivolts also, superimposed over 1 volt, which is a typical situation in the case of cathode ray oscilloscope. What kind of common mode rejection ratio your cathode ray oscilloscope differential amplifier which is placed inside should have, in order that error is less than 1% is easily computed from this kind of discussion. In order to see whether we have assimilated what has been discussed so far. Let us see this example 14. For the differential amplifier shown as indicated in the figure, okay, determine the common mode gain, okay, which we have been calling as AC. The differential mode gain, which we have been calling as AD. The common mode rejection ratio in decibels. The differential mode input resistance. The common mode input resistance. We will call these things as RI differential and RI common. So, this is something that we have not yet studied, but we will see that we know the technique of splitting this pair into two separate circuits, okay, either for common mode signal or for differential mode signal, and then we know how to evaluate input impedance, etc. So, the same technique is therefore adopted now. So, let us now consider this circuit. This is grounded, let us this is grounded, okay, quiescent wires. Okay. And this is 0.6 volts and this is minus 10 volts. So, the drop across 9.4 K is 9.4 volts, and therefore, the current in this is 1 milliampere. Is this clear? So, this is 0.6, this is minus 10 volts, the drop across 9.4 K is 9.4 volts, and therefore, the current in this is 1 milliampere. And therefore, the currents in these two transistors will be, because it is symmetric, okay, 0.5 milliamperes each. Okay. This we have understood, that the quiescent current of each of these transistors will be 0.5 milliamperes. So, the RE for the transistors will be, okay, instead of 26, henceforth we will use 25 for computational is, okay. So, 25 divided by 0.5 is equal to RE. So, VT by IEQ. So, we will take this as 25 divided by 0.5 milliamperes, 25 millivolts divided by 0.5 milliamperes, which is 50 ohms. This is equal to RE of. So, GM is roughly equal to 1 over RE, which is equal to approximately equal to 40 millisiemens, or sorry, it is equal to 20 millisiemens, because it is 50 ohms. For 1 milliampere it is 40, okay. For 0.5 milliamperes it is 20. Now that we know GM, we know RE, we are in business. So, let us first find out the common mode gain. What is the common mode gain? We have seen that common mode gain AC equals minus RC, okay, divided by RE plus 2 RE. In this case it is, how much is that? 10 K divided by RE plus 2 times RE, 2 into 9400 ohms. So, strictly speaking, this is roughly equal to half, right, 0.5. How much is it exactly? 5 3. That is the common mode gain, minus of course. The sign indicating there is an inversion. So, this is 0.53. The differential mode gain is equal to, now this depends whether it is single ended or differential. Since nothing is asked, we will give the single ended output. So, single ended. So, minus Gm into Rc by 2 is equal to minus 20 millisiemens into 10 K divided by 2, which is going to be minus 100. Okay. So, the common mode gain is minus 100. Okay. Then common mode rejection ratio equals AD by AC, which is 100 by 0.53, which is around 200. How much is it? 188, which is a pretty low common mode rejection ratio, right. In terms of decibels, okay, it is 20 log to the base 10 of 188. So, please find out this log to the base 10 of 188, which is going to be 45.5, okay, decibels. Then we would like to find out the differential mode input resistance, RID. In the differential mode operation, we said emitter is grounded. Okay. So, emitter is grounded, we have concluded. Therefore, these are two different common emitter amplifiers, and therefore, common emitter amplifier, the input impedance is RE into beta plus 1, because we are looking at the input from the base. Okay. So, which is 100 into 50, which is 5 K. Okay. This is 100. Actually, let us put it this way. This is 50 into 100, which is 5 K. This is the case for one input VID by 2, but we would like to have it for, this is for VID by 2. VID by 2, the input impedance is 5 K. For VID, how much is the input impedance? So, VID, therefore, the input impedance is 2 times 5 K. VID by 2, the input impedance is 5 K. What we want is a differential signal is VID, not VID by 2. Okay. So, this is 10 K. Common emitter, right. Next, for VIC, it is again two individual stage with RE plus 2 RE in the emitter lead. So, input impedance is going to be, okay, how much is that? RE plus 2 RE into beta plus 1. This is for VIC. Is this clear? That means one amplifier is going to feel this much input impedance, another amplifier is also going to feel the same input impedance. Since VIC is supplying to two amplifiers, what will be the effect of input impedance? One amplifier, okay, is seeing this much input impedance, another amplifier which is connected to the same voltage is also seeing the same impedance. Okay. Now, as far as VIC is concerned, there are two such impedances connected to the same amplifier. Okay. So, what is the effective impedance seen? This impedance divided by 2. Is this clear? So, effective RIC, right, is going to be RE plus 2RE into beta plus 1 divided by 2. Normally, this RE is very small compared to 2RE. Therefore, effective, this is RE into beta plus 1. Once again, let us go through this. VID by 2 was seeing an impedance of RE into beta plus 1. Then how much VID will see? Okay, 2 RE into beta plus 1. Okay. Here VIC was seeing two such impedances connected in parallel. So, how much VIC will effectively see? This impedance divided by 2, and therefore, this is the, therefore, it has a common mode impedance component as well as differential mode impedance components. The differential mode impedance components, even though might be low, the common mode impedance component should be very high. Okay. Strictly speaking, therefore, common mode rejection ratio also is estimated by simply taking the ratio of the impedances. Okay. This RE divided by this impedance, okay, is going to give us the common mode rejection ratio. This impedance is 2 RE into beta plus 1. Okay. This is RE into beta plus 1. So, it is RE by 2 RE. Again, okay, it is going to be your GM into RC, okay, by 2, GM into RE by 2. So, this factor also gives you a measure of what? Your common mode rejection ratio. Is this clear? So, this completes the problem. Now, let us see how in a laboratory we can measure different common mode rejection ratio of a differential amplifier. Now, why I am telling this is, we actually came up with an idea of splitting any two given signals Vi1 and Vi2 as differential mode signal and common mode signal. So, if I have to apply a common mode signal to a differential amplifier, it is easy, right. I will not complete the thing. We will say we are applying VIC and VIC. What does it mean? The same voltage is applied. So, this is what is done. The same voltage is applied to both the bases, and the output is measured, V01 and V02. So, same output voltage is, same input is applied to both the bases, both the bases are connected together and same voltage is applied. That is why we actually had a current which is this current plus this current. So, this voltage VIC divided by these two currents which are one and the same, okay, resulted in half the effective output input impedance, right. Okay. Now, measurement is easy as far as this is. If I want to measure AC, I measure V naught 1, change in V naught 1, delta V naught 1 by R, that is delta VIC. Okay. Or this is also going to be the same as delta V naught 2 by delta VIC. If these are identical, these two should be the same. Okay. I can therefore either measure this or this. These two will be exactly same. Okay. This is simple enough. There is no problem. As far as differential mode gain is concerned, I have to have a situation here of this type. This should be VID by 2, and this should be having a phase shift of minus 180 degree, that is, this should be minus VID by 2. How do I get it? It is not very simple. I should use a transformer, okay, or generate a phase shift of 180 degree and then apply. This is not necessary. That is why I wanted this is not necessary. What I do is I apply simply VID to one end and ground this end. This is not strictly differential mode. This voltage is 0 and this is VID. Okay. So, what happens now? The output is AD times VID plus AC times VIC. This is actually the output here. This is not 0. VIC is not 0. What is VIC? VIC is 0 plus VID by 2. So, this is going to be AD into VID plus AC into VID by 2. Okay. So, this is what is going to be measured in this. If I measure the output here or here, it will be the same in magnitude, but opposite in sign. So, whether it is this or this is going to be the same. Okay. So, delta V naught 1 or delta V naught 2, okay, delta V naught 2, okay, magnitude wise will be the same. But this is therefore is equal to AD into VID, which is wanted, into 1 plus 1 over rho half. So, the error you are committing is extremely small if the differential amplifier is having good CMRR. So, normally we are sensible enough to design good CMRR differential amplifiers, and therefore, this situation, this particular thing is always going towards 0, and therefore, I can still claim to measure AD accurately, even though this has a common mode voltage which is VID by 2. Is this clear? So, this is the method of measurement without using the phase splitting arrangement or a transformer, which is good enough for accurately measuring AD in a good differential amplifier circuit. So, this is all I wanted to indicate, that in a good differential amplifier circuit, the input impedance also will correspond to only what? VID, that is the differential mode signal, and the common mode signal effect is going to be very low. Therefore, if you apply a single ended input, it is as though it is differential, okay, mode. You can consider as though it is a differential mode operation in a good what? Differential amplifier. This is emphasized in practical situation. You do not have to therefore apply the differential mode signal to a differential amplifier. You can apply, okay, input only to one end and still achieve good differential properties. Okay. Now, we are going to consider the differential amplifier in general for large signal. I am not going to assume any small signal model. We have assumed a model in the earlier situation that the common emitter amplifier can be replaced by its model, okay, which is VBE delta VBE into GM as a current source at the output. Okay. Now, we are not going to assume such models. Therefore, in general, for a differential amplifier, let us see how output versus input characteristic. That is, this time we would like to know the output versus input characteristics or transfer characteristic of a differential amplifier, how it looks like. This we had seen for common emitter amplifier, etc. Now, we would like to see the same thing for differential amplifier, transfer characteristic of a BJT differential amplifier. Now, let us consider the input VI1 and VI2. Strictly speaking, we are now considering only the differential mode signal. So, I will put it as VID by 2 and minus VID by 2. This is equally well applicable, I told you, when it is VID here and 0 there. Okay. So, if this is VID by 2 and this is minus VID by 2, what happens I would like to know. Okay. The current in this remains constant, that is important here, okay, at let us say I naught. What is the value of I naught? VEE minus V gamma divided by RE. So, this I naught is going to be VEE minus V gamma divided by R. Now, let us call this IE1, this as IE2, this as VBE1, T1, this is T2, and therefore, this voltage is VBE2. So, we know that VID equals VID, which is VID, this voltage between these two is VID, equals VBE1 minus VBE2 at any instant of time. VBE1 and VBE2 being instantaneous voltages, okay, across the base emitter junctions of the two transistors at any given time. Therefore, okay, this is VBE1 minus VBE2. Always, there is no assumption made whether the signal is small or large, it does not matter. This is always valid, clear. So, VID is equal to VBE1 minus VBE2. Next, IE1 plus IE2, instantaneous values of the two emitter currents, will always equal what? I naught. This is also always valid, Kirchhoff's law. Now, we also know that IE1 according to the diode relationship is IE naught approximately exponent, okay, VBE1 by VT, that minus 1 I am ignoring, the diode relationship. Then IE2 is approximately equal to what? IE naught exponent VBE2 by VT. This also we know at any instant of time. no approximation involved, except that it is made that -1 is ignored. Now, therefore, this is an important relationship in integrated circuit. What is it? IE1 at any instant of time by IE2 for two transistors which are identical. Identical in the sense they have the same IE naughts. Okay, is always equal to exponent VBE1 minus VBE2 by VT. This is an important relationship. The most important relationship I can ever think of in integrated circuit, because just because the two transistors are identical, okay, the ratio of the two currents of the two transistors will be an absolute constant, okay, which is independent of the parameters of the transistors, only equal to differential input VBE1 minus VBE2 divided by VT, exponential of it. Okay, that. So, what is VBE1 minus VBE2 in this case? It is nothing but VID. So, in this case, this relationship is valid always in general. Okay? Let those transistors be anywhere in a circuit. Let those transistors be anywhere in a circuit. The ratio of the two currents of the transistors will always be equal to VBE1 exponent VBE1 minus VBE2 by VT. This is a general relationship. In the case of a differential amplifier, we know that VBE1 minus VBE2 is equal to VID. In that case, it simplifies to exponent VID by VT. So, in a differential amplifier, okay, this is always valid. The ratio of two currents IE1 by IE2, which is same as what? IC1 by IC2, because alpha times, right? Alpha times IE1 by alpha times IE2 will be IC1 by IC2. Okay, is exponent VID by VT. This is valid for several decades of variation of the current. That means IC1 by IC2 may be a huge value or a very small value. This relationship is valid. There is no other device which satisfies such fantastic relationship up till now in electronics, right. I would like to therefore emphasize the fact that this is the most important relationship ever to occur in electronics. Okay. Now, we will have therefore, if A by B equal to R, A minus B by A plus B is equal to R minus 1 by R plus 1. This is the ratio relationship, you know. If A by B is equal to a ratio R, A minus B by A plus B is equal to R minus 1 by R plus 1. So, using that, IE1 minus IE2 by IE1 plus IE2 equals exponent VID by VT minus 1 by exponent VID by VT plus 1. What is IE1 plus IE2 at all times? It is a constant current I naught. So, we will replace that. IE1 plus IE2 equals I naught. Beautiful. In this equality now, IE1 plus IE2, the summation of the instantaneous values of these two currents IE1 and IE2 will always be equal to I naught. And IE1 minus IE2 is equal to IC1 minus IC2 by alpha. and look at this Vc1 okay, minus Vc2 is V naught okay, and V naught is equal to Vc1 minus Vc2 and Vc1 is equal to Vcc minus Ic1 Rc and Vc2 is equal to again Vcc minus Ic2 Rc, which will tell us that this is equal to Ic2 minus Ic1 into Rc. And therefore, we can rewrite this equation as IE1 minus IE2 is IC1 minus IC2 by alpha into I naught, IE1 plus IE2 being equal to I naught. This is equal to the exponent VID by VT minus 1 by exponent VID by VT plus 1. If I multiply this now by RC, this also I can multiply by RC. This factor IC1 minus IC2 into RC from this is nothing but minus V naught. So, this is minus V. So, we get V naught equal to minus alpha I naught RC exponent VID by VT minus 1 by exponent VID by VT plus 1. So, this is an important relationship between the output and input of a differential amplifier. Now, let us look at it. When VID is large negative, this factor will go towards 0. This factor also goes towards 0. So, this whole thing becomes minus 1. So, it will be minus into minus. So, plus alpha I naught RC. So, that means when we can plot this here, V naught versus Vi, it will start with alpha I naught RC when VID is large negative. Now, when VID is large positive, this is very large compared to 1, this also is very large compared to 1. This whole factor will go towards 1, and therefore, this V naught will go towards minus alpha I naught RC. That means, the other asymptotic approach is alpha I naught RC when VID is large positive. In between, what is that? When VID is very small or 0, this is going through 0 because this is 1, this is 1 minus 1, so 0. So, it is passing through 0, and that plot actually speaking is going to be something like this. This is a well known plot. This we can write in the following manner: alpha I naught RC VID by VT. So, I can write it as multiply both sides by exponent VID minus VID by 2 VT, okay, numerator as well as denominator. So, what do you get? This will become VID by 2 VT, this becomes minus VID by 2 VT, this will become this, and this will become exponent minus VID by 2 VT, which is going to be nothing but, this is nothing but hyperbolic tan function. minus alpha I naught RC tan hyperbolic VID by 2VT. So, this function which is going from alpha I naught RC to minus alpha I naught RC is nothing but, okay, strictly speaking, minus alpha I naught RC tan hyperbolic exponent VID by 2VT, that is the exponent is removed, VID by 2VT. Is this clear?